So I am going to start about talking about enthalpy. And enthalpy is essentially quite more important description than the actual internal. I mean, both are important. But think about, this is a system under constant pressure, right? So this is the one when they have a movable walls, right? If it is some kind of closed bottle, that's a bomb system that will constant volume. Whereas you have something that can adjust, and that's a movable, and this is under constant pressure. Is your body is under constant pressure or constant volume? Your body is under constant pressure. I don't know if you guys ever seen the movie. It's very old, Total Recall. Have you seen that? When you go outside in the Mars, what happened to the person? They become balloons, right? It is they're trying to adjust to the outside of the one. So our skin is movable, they're inflatable. So many of the system is a more realistic system is under constant pressure. And obviously styrofoam cup that you did in your XChem 1, that's constant pressure too, right? So this is important to have a system not constant volume but under constant pressure. And so that's the one starting point. So first thing, the same drill here. Pressure is only function of temperature. Enthalpy is only function of temperature for ideal gas. And for anything that is non-ideal real, still temperature is a main factor. And I will choose the pressure as my other peak to variable. And that's a non-ideal. Okay, so it's a non-ideal gas. I have to consider, once again, intermolecular distance, which has an interaction level, internal energy depending on those. And how is that defined on H? And this H is actually defined, I think this is even has been repeated in many times in your learning of the chemistry from high school to the freshman chemistry. This equation. You cannot miss, right? You cannot miss that. But now this is my last opportunity for you to remember what's the meaning of this. This is an internal energy. Okay, I got that. What is meaning of PV? That's another form of an energy that you should consider for the system. That's what I'm saying. Okay? So when your system can undergo the volume change, the volume times the pressure should be sort of another form of an energy that we should consider, and that is why we call H is not just a constant volume case, but something that when you change your volume and the pressure at any condition, this is all the definition of it. And once I have this simple equation like this, I'm in business to do something like here. Take the differential, right? du dp times v. So do you remember your calculus class? If you take the derivative of two functions, what do you do? Derivative and times g. Do you remember this? So that's the same thing that you have to do it here. Okay? So what I'm going to do is I'm going to copy down the du. But here I'm going to put p times dv, keeping v constant. That is equation. So this is our first equation that I know. What about the second equation? You know the du q plus w? That's right? Yeah. And then I can dq plus dw, whichever, okay? dq, and then this one, I put a reversible word as 1, so p times dv. I do do this. And then I put that in, because that's a du from the equation 2. And then I finally got this form. Enthalpy change is dq. This is gone, and that's the one. This equation is not so useful, but it's some sort of the form that to ultimately get to where, so now where when IP is constant, it means is pressure change is 0. Okay? This is 0. And so, pressure constant, dp 0. I have one last operation to do left. You know what? Here, right? What do? You write P. This is what you write as a subscript. So therefore, you will be. This is the only equation that is needed to remember. That's it. Enthalpy changes heat supply under constant pressure. Remember? Delta U is heat supply under constant volume. Right? So what that means is, if your system has a movable wall, right? Something that can moving up and down, and if you apply the heat, and if your system has a fixed wall, with a heat, and the heat supply here was provided in a form of QP, whereas this is in the form of QV. So this is something that people can design and then they can do the experiment. And so therefore, I can define my DH. And so the CP here is enthalpy change. What? I don't like this one right first. Something that I can deal with, something that I measure QP. Let's say I just measure delta T, right? And do it a bunch of times. And if you do that, you can measure the heat capacity of the place. So constant pressure, and this is an experiment that you can measure that. And mathematical form. This is what they write under constant pressure. This is what they write. And so does here. CV, QV. So this is a contrast. So far, so good. Any questions? So now I'm going to do a little trick on this. So I'm going to bring this card over. Let's suppose this is an ideal gas. And then what it looks like this. This one is same as for you to write. All right. So PV called nRT and then the U. So that's for the ideal gas. Right? So why this one comes in handy is because for number 3, delta H versus delta U in ideal gas. If you think about that, because of that relationship, is actually 1 meter is a gas, and delta H is delta U plus N gas times R. So this relationship is defined. And delta G, or delta NG. Okay? So delta N gas is gas in product. If I subtract it, gas, number of gas in the So 2H2 gas, O2 gas, 2H2O. So let's think about it as an example here. Okay. So what is my delta N of gas in this reaction shown up here? How many moles of gas do you see as a product? How many moles of gas see a product? That's right. Somebody say 0, and it is right. No gas. What about how many in the reactant?
3.
3, right? 2 plus 1 is 3. So that's a minus 3. So therefore, in this case, delta H, delta U, minus 3 on. So that's the case particularly for this reaction. Okay? This reaction, this reaction. Okay. Number 4, heat capacity. So because of the system is under constant pressure is much more common. So this value is actually quite tabulated a lot for a lot of different materials. Okay? And you can see that you can find it in the back of the textbook. And I like to start with something obvious. Cp is actually depending on the number of moles. So it's actually, we need to define Cp molar. It's the heat capacity under constant pressure divided by number of gas in that system. Okay? If you double the volume, it takes twice the heat to increase the same amount of the heat. So this heat capacity actually depending on N. So you have to divide it, and this is a molar heat capacity, and that's what make this one useful. Molar heat capacity. You can continue to be under constant volume, on the constant pressure. It's a long name, but it's what this one is. And why am I showing this is, okay, I think the first thing that I know, Cp, enthalpy change, measuring temperature, and I can do that. This is something that I can do. For CPM can be constant. CPM cannot be ever constant. If you think about it, I told you about when you change the constant, it can be constant for temperature. I'm just talking about temperature dependent. It's temperature window or temperature window of interest. Okay, so I'm doing this experiment and changing the temperature from, I don't know, 25 degrees C to 100 degrees C. You know, they have a different movement of the energy. So they should have a different heat capacity. Okay? But if it is, then your life is complicated. Right? So what you do is it's not a bad assumption that they are constant. And then it's going to be okay. There are even, so this is true for most of the gas, unless you have a change like, from here to 1000 Kelvin, within this 100 degrees C, 200 degrees C, it's about constant, and they even put you the heat capacity value for some kind of many gases as a fixed number. Okay? So that's what there is. And this is typically for gas. Okay. CPM is actually A times UT C times 1 over T squared. Okay. This equation works for liquid, solid, and stuff. Because it does have a pretty complicated dependence, and they choose to provide it this way so that they can capture all kinds of temperature dependence by tuning this A and B, C values. There's no science here. They just provide, it's a temperature dependence. Let me throw the term that is when you increase the temperature, this one increases. When you increase the temperature, actually this one decreases. So you can have a two term that you can kind of fuzzy factor that you can fit that in. And this one is actually works well for most of the case for limited temperature window of your interest, so that they provide this ABC value, and you will find that in the textbook too. Okay. So why am I saying this? All this thing is because I am interested in delta H. I mean, this is what I want to know, and I want to have a predictive knowledge. How much heat do I need for me to change this mercury from room temperature to 100 degrees C, or block of metal from this temperature to the other temperature. And if you look at that, this one, right, is this one times that. Right? So dH